All right, so now that we've gone over the selection rules for UV visible spectroscopy, let's analyze our first transition metal complex. So here's an example, is the titanium 3 hexa aqua complex. And so this is a D1 complex. Titanium is in group 4. Titanium is in the third oxidation state here because water is a neutral ligand. And so we've removed 3 electrons from something that had 4 electrons to start out with, so that gives us 1 left, or D1. So we can draw our simplified molecular orbital diagram, and all I'm showing here are the T2G and EG states. Why just these states? Because these are only the states that are going to be within the UV visible, or within the UV visible range. The other states are going to be in the deep UV, because we know that d orbitals are close together in energy. Those molecular orbitals that come from d orbitals are going to be close enough in energy that they will be probable by UV visible spectroscopy. Bonding electrons that are way down from p and s orbitals, those are going to be in the deeper UV, and we're not going to see them in a typical UV vis experiment. We'll have to go to photoelectron spectroscopy, higher energy light, to see those. So our ground state is going to have 1 electron in the T2G. Of course, the gap between the T2G and the EG defines delta O. We're assuming this is an octahedral type complex because we have six ligands. All right, so we can write the term symbol for this ground state. This is going to be doublet T2G. How do we do that? Well, remember, this is a doublet, 1 unpaired electron, and it has the same symmetry. Doublets have the same term symbol symmetry as whatever the symmetry is of the orbitals where that electron lies. So it's in the T2G, so it's a T2G symmetry, doublet T2G. Now we go ahead and shine light. Well, we're going to have an excited state. That's going to pop up an electron into the EG. And again, this is a doublet, and this time the symmetry, the term symbol symmetry, is going to be doublet EG. And so we have one transition here that we've identified, doublet T2G ground state going to the doublet EG excited state. That is spin allowed because we're going from a doublet to a doublet, and it is Laporte forbidden. Why is it Laporte forbidden? Because we're going from G to G. We did not change parity, right? G to U or U to G, that would be Laporte allowed. And so that from that prediction, we should get 1 peak in our spectrum. It should be pretty weak, between 1 through 1,000 inverse molar inverse wave numbers in terms of the absorption coefficient. You can see it ends up being absorption coefficient of about 5, and there is 1 general peak. So that seems really easy, and it is. It all works out for this transition complex. Now you'll notice this is split, right? There's actually 2 peaks here that are very close together. Why is that? Jahn-Teller distortion. D1 complexes are triply degenerate, and so there's going to be some Jahn-Teller distortions. That's going to give rise to 2 different states that we can access here in the EG, okay? So that seems pretty simple. We're able to go on to our next complex, and our next complex is going to be a vanadium 3 complex. Same thing, we just marched over 1 on the periodic table. Vanadium is in group 5. Vanadium 3 plus here, so that's going to be D2. Okay, great. So let's just do the same thing that we did before. And we have now a triplet, right? And so you might think, well, there's 1 gap here, so we should have similarly, 1 general peak. Maybe there'll be some Jahn-Teller distortion, but 1 general peak. And that turns out to just be totally wrong. There are 3 peaks. 1 at 650, 1 at 400, and 1 at 250. Why is there not just 1 peak? And the answer is that things get very complicated with electron-electron repulsion. You can have many different states here. You do have many different states due to the interaction of these 2 spins. It's just like when you learn in quantum chemistry, introductory quantum chemistry. Once you get to a helium atom and you have 2 electrons, you can't solve the Schrodinger equation exactly, right? Things just get complicated with electron-electron repulsion. And so the whole rest of this, most of the rest of this chapter is all going to be about accounting for this electron-electron repulsion. And at the end of it, very end, after many videos, we are going to be able to understand why we have three peaks and not just one, and totally account for this electron-electron repulsion. So let's get to it.